Section 2.6 is on page 161. It talks about implicit differentiation. So something that we're used to, we've been looking at y equal all along. When I say find dy dx, well, basically, you're not thinking much about it. You're just writing dy dx equal, you bring the power down, subtract from the power. Up till now, we've been dealing with a dependent and an independent variable. The dependent has been on one side, and every time you took a derivative is d dx of this y you applied the rule on the independent variable. An exception to that came up when we started doing the chain rule, when we had u depending on other variables than x and we wanted to find the derivative of x. Now, for example, if they were to take this problem and just get everything on one side and 0 on the other side, isolate one equation on one side, everything else on the other side, when you would take d dx of both sides, well, the right side is simple. The left side, that is your dy dx, and since this is matching, then you would simply say, well, that's bring the power down, subtract from the power. And then you can solve for dy dx and everybody's happy. Of course, you could solve for y, but that's not the point, because pretty soon we're going to get to functions in which you can't solve. And similarly, if they were to use the y to the right, if you were to take a derivative of this, so it does matter you're taking a derivative with respect to what. And here, when you look at that, you say, all right, y negative plus x squared, this is a 0. Since this doesn't match that, I ignore the negative, and the derivative of a y is dy dx. And since this matches, that's simply 2x. I have another example. If I wanted to look at this example right here, if y was the sine cubed of x, and I said, still find dy dx, dy dx would be, bring the power down, subtract 1 from the power, times the derivative of the inside by the chain rule, times the derivative of the inside is cosine of x. And what if I was to say, you know what, I messed up, it wasn't really cosine, it was tangent. Wouldn't you say dy dx still, that is 3, bring the power down, subtract 1 from the power, and derivative of tangent is secant squared of x? There it is, everybody's happy. And of course you're correct. What if I was looking at y equal, don't you bring the power down, subtract 1 from the power no matter what that is? And then times the derivative of the inside. What's the derivative of the inside? You're taking d dx of x to the 4th plus 2x plus 1. Since these match, that's your traditional derivative, which is 4x cubed plus 2. Now, here, we took the derivative of that. What if I told you, you know what, y equals z cubed, and you're asking me, okay, but what is z? I'll say, well, z could be, z is either the sine of x, or the tangent of x, or x to the 4th plus 2x plus 1. One of 3 choices. And I'll say take a derivative. And of course, your question is, wait a minute, but shouldn't you tell me which one of those 3 it is? And what if I refused? What if I said, you know what, I'm not going to tell you that, but I want you to take a derivative? Well, then you gotta think a bit. You say, you know what? Okay, you know what? I just took the chain rule. I'll tell you what. I know that z is a function of x. So I know that z is either the sine of x, the tan of x, or x to the fourth. If I let u equal z, then when you take a derivative, I'll say, well, that then y will become u cubed. The derivative of y with respect to x, that's what I want. Y depend on u, and u depend on z. Okay, I said it right, I wrote it wrong, you know what I mean. And u depend on z. Well, let's see how that works. If I take a derivative of this, that is 3z squared. Wait a minute, I knew that. I did that here. I did that here. I did that here. I really don't need to do this. Times the derivative of u with respect to z. And we said let y equal z, which is f of x. Right? So wouldn't that be the change in u with respect to x? And then when you substitute back in, that's 3z squared times dz dx. Well, let me take this problem and elaborate a bit more. Just a bit. Or, forget all of this. Couldn't have I said, take this out, I really don't want that, and I don't want that z. You are claiming y equals z cubed. Not a problem. If you want me to take a derivative with respect to x, I need to know what z is. If it is sine, I know what to do. If it's tan, I know what to do. If it's x to the fourth plus 2x plus 1, I know what to do. If you're not going to tell me, that's going to be 3z squared, right? Times. Whenever you decide to tell me what this z is, take a derivative of that with respect to x. So, if z happened to be a sine, take a derivative of sine with respect to x. If z happened to be a tangent, take a derivative of that with respect to x. And it's happened to be x to the fourth plus 2x. Take a derivative of that with respect to x. So this is one way. A student showed me a trick that I want to share with you. A student once told me, you know what, look, this is how they were taught, and I really liked it. They said if you're going to take a derivative, that's dy. Since you see a power function, bring the power down, subtract 1 from the power, times dx, and derivative of a constant is 0. They said that was the best way they were able to deal with this. And once they figured out what they want the derivative with respect to, when they said dx, they divided each of those by dx, and this became dy dx minus 2x, and here they canceled out, and that's it. So this idea of implicit is a bit annoying in the beginning. If I wanted to do it on this problem, they say, you know what, before you even think about all of that, just take a derivative, dy. When you want to take a derivative of a power function, you bring the power down, subtract 1 from the power. I have 3 examples right there you could look at. That's what you do every time. Times the derivative of the sine of x. Right? And now you will decide, okay, well, how do you want to do this? Well, if you decided to do it with respect to x, this is all one term. Then dy dx will be 3 times the sine of x squared, and the derivative of sine is the cosine of x. Actually, I should have done an extra step, but that's okay. I'll play it on the next set of problems. So be careful how this game is played, because this will change from problem to problem. So when I look at this problem here, it says find dy dx. If I want to follow this trick, then derivative of a power function, bring the power down, subtract 1 from the power, dx plus the product rule. derivative of the first times the second plus the first times derivative of the second. I have all the space in the world, but I keep squishing things in. Derivative of a power function, bring the power down, subtract 1 from the power, times dy equal 0. And now since they want it with respect to x, divide each term by dx. Remember, this is all one term, so if you put a dx right there, and a dx right there, and a dx right there, these cancel out, you're left with 4x plus this you distribute in dx over dx, that becomes a 1 times y plus x, and dy over dx, that would be dy dx minus 2y dy dx equal 0. And now I need to solve this problem for dy dx. I need to leave this by itself. If I move those two to the right hand side and factor a dy dx, I'll have an x left minus 2y equaling negative 4x plus y, and dy dx equal negative 4x minus y, not plus y. You guys be careful. Divided by x minus 2y. Of course, you could take a negative out if you wish. You don't have to. And there it is. And if I went back to the same problem, but I altered the game on it. Well, a power function. Bring the power down, subtracting from the power, dx, plus the product rule. Derivative of the first times the second, plus the first times derivative of the second, minus a power function. Bring the power down, subtract them from the power. And now you say, well, we want it with respect to x, so we're going to take, dy of both sides, and that is 4. Since those don't match, that will be the x dy plus, and here you're gonna get a d1 over dy distributed into this, that is dx dy times y plus, and here it'll cancel out. Dy over dy on each other plus x, and here dy over dy will cancel each other out, and there it is. And now you're going to solve for this instead. So you're going to move those two to the right and factor a dy dx out of both of those. So that will be dx dy for x plus a y, and on the right hand side I'll have x negative x plus 2y, and dx dy would be negative x plus 2y divided by 4x plus y. Alright, now if I really wanted to go back to that first one and fix it, when I took this derivative, I shouldn't have stopped there. I should have said by the chain rule times the derivative of sine, which is cosine of x, dx. That's what I should have did. And when I take a derivative with respect to x, this is all one term. Those cancel out. That's what I need to see. But you know what? Okay. Of course, you don't have to do any of this. You could just use the box method. For example, take a derivative, bring the power. So you want dy dx all throughout. That's 3x squared minus the product rule. Derivative of the first, well, that's 1 times the second plus the first times, what's the derivative of y squared? 2y. You could write y prime when you become comfortable with this. What's the derivative of y cubed? Bring the power down, subtract 1 from the power times. Since that doesn't match a y prime, equals 0. And now you want to solve for y prime. Algebra. So if I factor a y prime out, I'll get negative 3x squared plus y squared divided by negative 2xy plus 3y squared. continue in the next video.